In this board, we will see few more morphological algorithms, the continuation with the previous board, morphological algorithms. So, this is the thickening morphological algorithm. The expression for thickening is defined by the expression A union A tensor multiplied with the tensor product with the B. So this is the expression we are defining the morphological thickening operation. The thickening of A by a sequence of structuring elements. So here the B is a structuring element, which is a sequence of structuring elements. Suppose we are taking here the single, here the sequence of structuring elements. Then we expressing A tensor product with the B1, tensor product with the B2, and so on, tensor product with the N. N is the sequence number. So we usually the usual procedure is to thin the background of the set and then complement the result. First, we have to do the thin morphological operation on the background of the set and then complement the result. This will giving simply the thickening operation. Here see some example. So this is the set A and the complement of A means the complement of this is this one, A complement, and result of thinning. So first we are thinning. So result of thinning operation is we are getting this one from this. Okay, then after thinning it, thickened set obtained by complementing this. Okay, so by the complement the result, then thickening operation is this, the complement of this. Okay, and final result with the no disconnected points, with the no disconnected points. See, this is a disconnected point, this is a disconnected point. With the no disconnected points, result is this is the output. So this is the thickening morphological algorithm. Now see another skeleton's morphological algorithm. A skeleton S of A. The skeleton is represented with the S of A. Of a set A has the following properties. These are the properties. So when we want to apply the skeleton, then these are the properties we have to apply. These properties should be satisfied. So if Z is a point of S of A and D of Z is the largest disk centered at Z and contained in A, one cannot find a larger disk containing D of Z and included in A. I'll explain this more with more explanation elaborately. If Z is a point of S of A, so within the skeleton, A is a set, you know, and the skeleton representation is S of A. Within this set A, some point Z is there. So Z is the element of within the A, and D of Z is the largest disk centered at Z and contained in A. So D of Z is the largest disk centered point. Largest disk centered point. See here, this is the disk, this is the disk, this is the disk, So in this part, this is the largest disk, and for that largest disk, the centered point is this one. So this is the Z. Then this is D of Z. Okay, which is also in A. This is A set. So we identified, we marked the largest disk, and we marked the centered point Z. So this is also included within A. And from this, one cannot find a largest disk contained D object and included in A. So we one point which we cannot find largest disk contained. So within this, another largest disk we cannot find. Within this disk D, another largest disk we cannot find. And within this disk D, the largest disk contained within this we cannot find. So a largest disk is contained in A, but within the disk we cannot find another largest disk, which is again contained in A. That is, the property should be satisfied for the set A. Then it is a skeleton operation of the morphological operation. Another property. And the disk D of Z is called a maximum disk. So a disk which is not containing another largest disk, then that is called the maximum disk. And the disk D of Z touches the boundary of A at two or more different places. The disk D of Z touches the boundary. See, this disk touching the boundary at two or more points. Here it is touched the boundary. It is here also it is touched the boundary. Here also it is touched the boundary. Here, okay, that is another property. So if these two are satisfied, then it is the skeleton operation. So here see an example. This is the set A, and various positions of maximum disk centered on skeletons of A are these: this one, this one, this one, this one. And another maximum disk on different segments of skeleton of A are marked. So from here another disk, from here another disk. In this way it is marked. Then complete skeleton is given by this. This is the output. Then for this we need to express it in a mathematical form. So how we can express, how we can define in a mathematical expression. The skeleton of A can be expressed in terms of erosion and opening operations. This is expressing by using erosion and opening operations. So S of A, skeleton of A, is equivalent to union of K is equal to 0 to K S of K of A. So all the skeleton operations we are doing union. Okay. But the K is equal to, this K value is equal to maximum set of K such that A symmetric difference of K into B, which is not null, not equal to null. Okay, so the K belongs to A symmetric difference with KB. B is the structuring element. So the K belongs to this one, and guarantee an element is there within this operation which is not null. There should be an element belongs to this. So Sk of A is equal to asymmetric difference of KB minus asymmetric difference with the KB. Circle B. Okay, so this is the expression where this B is a structuring element, and the structuring element of this is asymmetric difference with B, symmetric difference with B, and so on. So K successive erosions of A, and we can see the example. So implementation of equation, this equation we are implementing in this here, A symmetric difference with KB. This is okay. So the original set is at the top left, uh, and its morphological skeleton is at the fourth column. The reconstruction, so these are the morphological skeleton operation. Okay, so this is for this is the S of A. For this is the S of A. Okay, and the reconstructed set is at the bottom of the sixth. Okay, so in this way, and this is the structuring element. Now the reconstruction A can be reconstructed from the subsets by using the expression union of K is equal to 0 to K S of K of A plus circle with the K of B, where S of K of A plus circle with K of B denotes K successive dilations of A. K successive dilations of A. Okay, so this is the reconstructed subset equation expression. So here we can observe all the reconstructions upon structuring element. We can see here, and final output is this. And now we will see another basic morphological algorithm, which is pruning. Now pruning morphological algorithm. So when we doing thinning and skeletonizing morphological algorithms, these thinning and skeletonizing tend to leave parasitic components. What is meant by parasitic components? So the parasitic component means some that is processed by an electrical component, but which it is not desirable for it to have for its intended purpose. Means it is leaving some resistance or some inductance or some capacitance. Okay, and that is which is not desirable. Okay, which is not desirable. So when we are doing thinning and skeletoning, a not desirable means parasitic component which is coming from the electrical components, because the computer is a digital device which is using some electrical components to form the circuits and motherboard and everything. So by those parasitic components are leaving, means when we are doing thinning and skeletoning, there exist some parasitic components. So the solution for this is a pruning method. So these pruning methods are essential complement to thinning and skeletonizing procedures. So what is pruning? Pruning is a horticultural and silvicultural practice involving the selective removal of certain parts of a plant. So, within the plant, such as branches, buds, or roots. So, within the roots, or within the buds, or within the branches, the parts of the plants, within their parts of the plants, uh, selective removal, whatever we want to select and remove from the branch or from the bud or from the root or any part of the plant, we can do by the process of pruning, that is called the pruning. Now I'll show you an example for the pruning operation. See this one. So this is the example for the pruning. First, this is the original image. Okay, and this is the structuring element. So the structuring element sequence is B1, B2, B3, B4. These are rotated 90 degrees. And other four structuring elements are B5, B6, B7, B8. And so the structuring element is a set of 8. Is total 8 structuring elements. The set of sequence of 8 structuring elements. So the pruning operation first we have to do is x1 is equal to a tensor product of set of B. And then after this operation, see here, one second, yeah, see here, after doing that operation, then this is the structuring element used for deleting endpoints. By using these structuring elements, we are deleting endpoints. Then the result of 3 cycles of thinning. The thinning operation is this, and 3 cycles of thinning. The result is as this one from the original one. This is the original one. After doing 3 cycles of thinning operation, this is the resultant one, and this is the formula. Okay, and then the endpoints of the dilation endpoints, by applying this equation by the 3 by 3 structuring element, this is the endpoints identified by the thinning operation from this step to this step. And after that, see here, so this is the dilation of endpoints. The dilation formula is this one. So this is the x1 and this is the x3. The dilation of these three union giving this. So this is the dilation result. And after that, after the dilation, means by the union of x1 and x3, the pruned image, the pruned image is this one. This is the pruned image. So in this way we will do pruning. Another basic morphological algorithm is morphological reconstruction. So we are reconstructing something. To reconstruct the image using morphological algorithm, it is one kind of morphological algorithm. It involves two images. Up to now we have seen one image and one structuring element. But here we are taking two images and a structuring element. Structuring element is compulsory. And one image contains the starting points for the transformation. One image we are using as the starting points, means first image containing the starting points. Those that image is for the transformation. So that image is called marker image. One image is called marker, which is having starting points, uh, that is for transformation. And another image we are calling it as a mask, constrains the transformation. So the second image, mask image, constrains the transformation. Then the structuring element is used to define connectivity between these two images, means the marker image and the mask image constraints transformation. The connectivity is given by the structuring element. And now see grayscale morphology. This is another kind of morphology method, which is grayscale morphology. And the grayscale image is represented with f of x comma y, you know this, and the structuring element in the grayscale morphology is defined with b of x comma y. So wherever we have a b of x comma y, it is a structuring element for the grayscale image, grayscale morphology. And non-flat, so this is the example. So a non-flat and a flat structuring element, suppose and corresponding horizontal intensity profiles through their centers, if we are taking, then the section based on flat structuring elements are look like this. The intensity profile, suppose this is the center point, we are taking the non-flat structuring element, then the intensity profile for this is this one. And now flat image, within the flat image, suppose we are taking the flat structuring element. So this is non-flat structuring element. So here suppose we are taking flat 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 structuring element, then the intensity profile is this one. Now in this grayscale morphology, the expressions we use, the mathematical expressions we use, so grayscale morphology, erosion and dilation by flat structuring. See, flat structuring. For this, the expressions we use is a f symmetrical difference with the b of x comma y. See, this is structuring element. This is grayscale image. Is defined as minimum of s comma t belongs to b, means s comma t belongs to structuring element f of x plus s plus y plus t, x coordinate, y coordinate, and f plus circle b of x comma y is equal to max s comma t belongs to b, f of x minus s comma y minus t. And if we applying this on grayscale image, so see, this is the example. I'll enlarge it a little. Now see, it is a grayscale X-ray image of size 448 by 428 pixels. Erosion using flat disk SE with a radius of 2 pixels is the resultant one. And dilation using the same structuring element, radius of 2 pixels, is this one. Now compare these three. It is by the erosion, it is by the dilation, and this is for the flat structuring. Now for the non-flat structuring element, the erosion is defined as f symmetric difference b of n is of x comma y is equal to minimum of s comma t belongs to B, f of x plus s comma y plus t minus B is a structuring element, B of n of s comma t. This is the set expression giving erosion for the non-flat structuring grayscale morphology, and this is the expression we are using for the dilation of grayscale morphology by non-flat structuring element. And the expression's duality, these two are duals in each other. We can observe here by duality law is applied here. Then the grayscale images opening and closing. See, the opening grayscale morphology opening and closing is f circle V is equal to f symmetric difference B of plus circle B. It is a structuring element. It is a grayscale image. So this is the opening and these expressions giving the closing. Okay, this is the cap symbol, and when we apply these expressions, then see, this is the intensity profile. Okay, upon this intensity profile, this is the flat SE structuring element, flat structuring element. Okay, and suppose this flat structuring element and it is the one-dimensional signal. It is the one-dimensional signal. The flat structuring element pushed up underneath the signal. Okay, push the flat. This is the flat SCA structuring element pushed up underneath the signal. Then this is the resultant one, and upon this we apply opening. This is the resultant one, and flat structuring element is now here, this one. And suppose we push it down along the top of the signal, then this is the resultant one, and from which it is the closing operation. All these are the flattening SE applied over there. Okay, and in this board we covered the topics: thickening morphology algorithms, skeletons, pruning, morphological reconstruction, grayscale morphology algorithms. Okay, we will see segmentation in the next board.